Okay, so we're going to write some exponential functions to model growth and decay, and does growth have a limit? That's what we're going to look at today. All right, and again, this is all 4.8, and it really is a lot of that project thing that I gave you a few weeks ago, it seems like. Okay, so here's kind of what the book does. Usually when I have done growth, I use pretty much the same equation that I do for the money kind of deal. So, but they use the one that's in here, they're using this. So we'll be consistent with what they're doing. And it's really not a whole lot different. So okay. So this, A of t, is some sort of like population that is growing, okay? A sub O is the initial, just like we had with the temperature when we did some of this before. E is E. K is a constant that usually represents some type of rate. And of course, T is time. So they might give you a population, or excuse me, they might give you a formula, or they might have you find a formula. All right, so for example, I'm looking here kind of at something that they have in the book. I'm just going to call it P of T for a population of something. Okay, so there it is. And then they're just going to ask you to analyze or give some, they're going to ask you some questions about it and just basically take a formula apart. All right, so for instance, they're going to say, hey, what's the initial value of this thing? What was the initial population, whatever this models? They might ask you what the growth rate is. We'll say this is a month thing. Okay, so let me make this down here a little bit better. So there we go. Here's our equation. Okay, we want to know the initial population, what the growth rate is, what the population is after 10 months. We'll say time is time, T is time in months. And then we want to know how long until this population reaches 350, because maybe that's some magic number for us. I don't know. All right. Good? Okay, let's go through it. All right, what's our initial population? Tell me, fire it at me. 200. Okay, that's that first number, right? That's our initial population. That's how it was when we did exponentials before. right there. Okay, growth rate. If we're gonna find a growth rate, how are we gonna find that? What are we gonna have to get? Well, we know this, right? We know that the initial population is 200, okay? And that happens when t is 0. Do we know what the population is when t is 1? How much? It might be, and it might not be, okay? It is a rate of growth of some type, okay? So it kind of depends on the equation and what that is. So you could be right, that it could be, but it might not be. So let's check this out. So let's see, how could we figure out what the population is after one time period? What would we do? Yeah, plug in 1. Okay, so you're going to go into Desmos, okay, go 200 E.043 times 1 if you want, and see what we get. And then let me know. How much? 209. Okay, so now we have two different populations, and they're consecutive. One's at 0, one's at 1. And this is an equation, so the growth should be consistent. All right. So now that we have two, how do we find the growth rate? Do you remember what we did? You could divide 209 by 200. All right. So let's do that. 209 divided by 200. Okay. What do we get? 1 point, what is it? 0.045. Okay, now we have to be careful because the question's asking us for the growth rate, all right, not the growth factor, because this number, remember, is the growth factor. That's how much it's growing by. But we want the rate. So how would we get the rate? What are we going to do with that? Find a what? Between what? You could, but you don't even have to do that. You can just find it, the growth rate, by looking at that particular number we just got. Okay, so here's what we're going to do. We're going to just chop off the 1. Okay? So Luis said, hey, I think it's going to be pretty close to that 0.043. And look at that. He was pretty close to being right. Okay? Yeah. Sometimes it's going to be really close to it. Sometimes maybe not. It kind of depends on the situation. But, yeah. There it is. So, when we want to go from factor to rate, the difference is just that it is, getting rid of the 1. And the reason for that is I'm kind of bouncing around a little bit. But this was the equation we used before. You don't have to write this down, might confuse you. All right, this is what we used before. And I said, A, that's your initial value, okay? And B is that growth factor. So what we found was the growth factor. Okay, that's what we got. But the rate, since this is growing, we're just going to subtract the 1 from it because this is like having 1 plus an R in there, where R is the growth rate. Okay? So see, this starts to look a little more like that money one. The only difference is that the R was divided by an N and we had an NX up on the top. Okay? That's what that is. So that's why we're subtracting 1 to get that R value. If it's a decay, we're going to do the same thing. All right? So that's what we did last time, and now it's kind of coming back. All right. So we got our growth rate, 4.5%. What is the population after 10 months? All right. Well, we can figure out what it is after 1 month. To do that, how do we figure out what it is after 10 months? What are we going to do? How did we figure it out after 1 month? What'd you do? Yeah, we just put the time in, right? Bless you. So that's what we're going to do. Okay? We're just going to put this time in here. 0, 4, 3 times 10. Okay? That's it. That's all we got to do. Put 10 in there. Yeah?
Where did you get the 109?
209? So what we did was we used this equation here. This is what they gave us, right? And we put in 1 for the time here. So I just wanted to, because we know initially that it's 200. Okay, we're trying to find that growth rate. So then we say, hey, if we put 1 in there, okay, that's going to tell us what it is after 1 month. And then we can do this division to find that growth factor. Okay, so we just put 1 in there. That's why now all we're doing is putting 10 in there to figure out what it is after 10. So what did you get? Drop in the decimal and see what you get. How much? 307. Okay. So after 10 months, we got 307. Okay. Cool. So far, all we've been doing is using this equation, all right, and just manipulating it. How long till it reaches 350? All right, so now what we're going to do is instead of finding or putting in the time and getting the population, we know what the population is, so we need to find how long it takes. All right, so it's going to be 200 e to the kt. But we know what k is. Sorry. 0.043 t. Okay, so there's the equation we got. All right. So we got to figure out what t is. What should we do? Great idea. Let's divide by 200. Okay, 350 divided by 200. 35, let's see. 7 over 4, 1.75. Is that correct? Okay, 1.75. All right, here's where you decide what you like to do. You know, are you going to use a definition, or are we going to log both sides because we've got a t in the power or the exponent? So that's our strategy. All right. So what do you want to do? You want to log both sides or use a definition? Somebody pick their strategy. Logging would be easier, okay? If we're going to log this, since it's an e, we're going to better use that natural log. It's going to turn out to be nice for us if we do. This here, we don't worry about. This pops out in front. Natural log of e is just going to be 1. And there we go. So now we just got, use decimals or your calculator, whatever you're doing to get the answer. So this would be a pretty good example of something you're going to see on Wednesday. It'd be a question, like this. Here's the equation. Tell me this, tell me this, tell me this, tell me this. Okay? What's t turn out to be? Should be pretty close to, not much over, should be over 10, but not a whole lot, because we were close to it, 10. 13? Okay. So you could use a definition, right? You can log both sides. All right. You could actually graph this and get an answer. Right? You could graph this equation and then graph this equation. See where they cross? So there's a couple things you can do on it. All right. I'm not going to tell you which way to do it. You just give me an answer and figure it out. All right. Any questions on what we did there? Make sure you ask. Don't hold back.
Just go over the growth rate.
Go over what?
How we found the growth rate.
Sure. So for the growth rate, okay, we got to have two consecutive populations, right? Because then we can see how they changed. Okay. So we already knew what the initial value was. Right. Good with that. So then let's go find the next one after. So after 1 on 6. So put 1 in for here and for t, and we ended up getting 209. Right. Okay. And then I asked, okay, how are we going to find the growth rate? And you just said, well, I'm just going to divide these. 209 by 200. And that's telling you the factor at which they're growing by. Now this comes from an equation. So that means that factor is going to be consistent. You could have put in 10 and 11. It doesn't make any difference. Okay. So here's our 1045. Right? Now, since this is when we did exponentials, and I brought my little temperature stuff in here, and we took the temperature of that hot water, right? We had all this time here, time, temp. So these are all our values, right? And I said, hey, we're going to divide each one of these. So we went around the room, everybody divided them, right? We came up with that. It was the K factor, but it was a factor. All right. Okay, this is what we got here. To find the rate, though, okay, the rate is different. So the rate, when we did those equations, this is your factor. These two things are exactly the same. All right. So the R is the rate of the growth. So for example, in a simple situation, if we have 2, 4, 8, 16, these just double. So the factor is 2. It's double, right? I mean, everybody can see that. But the rate is different. So if we took this number 2 and we subtracted 1, we get 100%. So that rate of growth is 100%. So there's a difference between the factor and the rate. Right? And that's what we did. We just subtracted 1 from it. And it is pretty close. And Lee said, well, he thought it was going to be this guy. Okay, and I thought, probably pretty close. Okay, That was good. Any more things we need to? Okay, so let's look at another one. Same kind of idea. And now we're going to have it to a negative KT. All right. I'm just going to say, well, okay. We'll just leave it as rate of growth, I guess. And and let's see, I need to give you okay. So there I gave you a K value. So initial value, rate of growth, population after 3 years, how long till half of original. Same deal, except this time K is a negative value. All right. So, what's our initial value in this case? What do we got? 100. Yeah, good. Okay, 100, right there. Nothing changes. That's always the initial value. That's 100. Okay. Now we want to find that rate of growth again. So we have, not the way you probably would write it, but at 100, 0 years. So how are we going to find the rate? What do we got to do? Do what? Yeah, plug in 1. Okay, figure out what happens after 1. Okay, so let's put 1 in here. So we're going to put 1 into this equation. 100 E. I'm just going to put a 1 there so you know what we did. Okay, put you in decimals. Tell me what you got.
Are you always gonna put one there?
Yeah, because, I mean, you could put 2 and 3 or 4 and 5. You just need something consecutive, but you already know what the initial value is, so you might as well just put 1. Okay? Because you just need 2 consecutive ones. That's all you need. What are we getting? 99.9. 9 what?
That's fine.
That's fine? Okay. All right. How are we going to find the rate then? What do we got to do? Well, not subtract 1 yet because we don't have anything to subtract 1 from. Remember, we got to find that growth factor first. So what do we do to find that growth factor? Yep. Well, that's easy because that's just going to be 0.9 9. All right? That's what it is. Now we're going to subtract 1. Okay? Now we're going to subtract 1. What do we get? Negative. What is it? Point what? 0, 0. 3 zeros and a 1. Yep, good job. Okay? That's what it is. Okay, so this should tell you something. First of all, okay, look what happened here. Start at 100, and this time we went down. So what is this particular population doing? Increasing or decreasing? It's decreasing. Okay. All right. Notice the difference is that this K value here is negative. All right. So that's what's happening. Our last time was positive. Okay, so it's decreasing. Okay, here's your rate of growth, which is negative, but that's because it's decreasing. So this would be actually the K rate. How small it is? It's not decaying by a whole heck of a lot. Okay, very small. All right. Let's see what happens after 3 years. So, what do we do to figure that out? Yeah, just plug that in, right? Okay, put that in there. Figure out how much we have after 3 years. It's not going to be a whole lot different than what we had after 1 year because it's not decaying by very much. Okay, what do we get? .6. Okay, again, wouldn't expect it to be a whole lot different. Thanks. How long till half of the original? So now we want to know how long it takes until we get half of that. All right, so what did we start out with? 100. Okay, so now we want to know, well, how long is it going to take? So half. So half of 100 is obviously 50. Going to put that there. Going to put this here. Figure out what t is. Okay, so see how this is just exactly what we just did. The only difference is that this one's going down, it's decaying, and the other one didn't. All right. So since it's the same thing, what should we do? What did we do last time? What are we going to do with this? Yeah, get rid of the 100. All right, good job. Okay. Going to get 0.5 there. And now you get to that point to where you got to ask yourself, okay, do I want to log both sides, or do I want to use the definition, or do I want to graph it? Your choice. Again, that natural log of e is just going to go away because the base is e, so and now we can figure out what the time is. If we get a negative value, then there's something seriously wrong, but the natural log of 0.5 should be a negative value. Okay. This should be a pretty good sized number, so when you get it, don't be surprised if it's a big number. Anybody get it yet? Well, that was good. 577? Okay. There we go. So growths have a lot, you know, with population things. Obviously, anything that grows is that grows. Okay, you know, disease, sickness, that kind of thing. Any population is going to grow. All right. Decay. All right. There's some good problems with decay. One of the things they do in here, they talk about radioactive decay, so you can measure. You guys probably seen that, how they measure the length, or like how old the bone is because of the radioactive decay and the half-life of carbon dating. Okay, that's all exponential. This stuff here we're using is that carbon dating stuff. Okay, you know, medicine. When you take medicine, it works for your body, but your body, you know, gets rid of the medicine over time. That's decay. All right, and you can look at that. That all can be modeled by this. Okay, so yeah. Questions on those two particular examples where they're giving you the formula and you interpret it. Okay. If you got your book, look at 352. Okay, at the very bottom, they talk about something called Newton's law of cooling. If you don't have your book, that's certainly okay. Because I'm going to write this out anyway, but at least you can see where it is. All right, so in Newton's law of cooling, they give you this, by the way, these are the same T's. They give you this formula, all right, where capital T is the temperature of the surrounding area. Use of O is the initial temperature. K is the rate, T is the time. All right, so let's do this. What I'm going to do is go back and see if I can find that temperature data. I think I have it. All right. I just have to go back and see if I can find it. I believe it's in here somewhere. There it is. Okay, so write down a couple of numbers here. almost break time. Let's do this real quick though. Let's see, 45.4. What is that? 0. Okay. And then 9 is 40.9 and 40.4. Let's see if I can make those work. I picked those because it's a little further down the line than initially. Okay. So, I'm going to try to write an equation for our data that we collected here. All right. So I've got u of t is equal to capital T. So let's see. That was in Celsius. So I'm just going to assume that's probably about 68 maybe degrees in here. So I think that's about 20, maybe 20 is more like 70. Let me see. I'll even look it up. Oh, it's dead right. Okay, so 20 degrees. So I'm going to put a 20 there. So I'm just going to assume that that's what it is. Okay. Plus U sub O, which is the initial temperature. So I wrote that down as 45.4 minus T again times E to the KT. So I know, here's my equation right here. All right. So not too bad. I pretty much know everything except I don't know what that K is. All right. I don't know what that rate is. So we're going to have to find that. The good news is that I also wrote down some other values. Okay. And I wrote down 2 of them. So let's pick one. Which one you want, the 9 or the 10 one? You guys can pick. 9, okay? How am I going to find K using that? Well, watch what we're going to do. So we're going to put 40.9 in for the U sub T, 20 plus 45.4 minus 20 E K 9. Because that time was 9, we had 40.9 for our temperature. All right, and we got to find K. So 40.9. Let's subtract 20 from this right off the top here. Okay, I'm going to subtract this what's inside the parentheses also. And see that every time it starts looking like the same thing that we had before. A lot of these problems, these exponentials, are all going to get you to the same spot. Here we go. I'm going to divide. Just like we did before. Nothing's changing there. Okay, I just need help on what 20.9 divided by 25.4 is. How much? 0.82? Okay. Now we'll natural log everything. Because I'm assuming that's what you want to do. Again, you could do it. You can graph it. You can definition. Okay, there we go. Again, they all look the same. It's just a different equation, but the idea is still the same. Okay, what do we get for K? Negative point what? O2. Okay. So what does that do? Well, that tells us what our equation is altogether now. All right, so that means we could ask, oh, well, gee, how long is it going to take to get to, 30 degrees or whatever you want. Okay, so U sub T is equal to 20. Again, that's what I'm assuming the temperature is in the room. There it is. If I type that equation in with the data that we had, should be a pretty good fit. All right.
Are we gonna have to know these equations with tests?
No, I would give you the equations. There won't be, I don't anticipate having a Newton's law of cooling deal on that. I'm just running through it. The ones that I would anticipate being on there are going to be like the one we just did with that A equals AEKT. Okay? But even then, I'd tell you, I have to give you some of the equation in general, right?
Same with today's quiz and the test, are we expected to memorize the financial models?
Nope, I gave it to you. It's getting to a point, to be honest with you guys, as an educator, if you don't know a formula, what are you going to do? Look it up. So I don't really know if it's that useful in a practical sense. I really don't. And I look stuff up all the time. As long as you're able to look at it and understand where you're going to put what the formula, what the values represent or the variables represent, you can put them in the right spots. That's probably what's important. Hey, what does this mean, and what do I put there? Okay. And does the answer make sense? That's my thing. Other people might not think that way. All right, I've kept you here long enough. So let's go get a break, and we'll come back. I want to do some more stuff with 4.8. We haven't gotten to our little simulation yet, and we'll do that. So I looked over example 4 in Newton's law of cooling, and it's pretty dang similar to what we did. They give you the temperature of an object after a certain amount of time and ask you when it's going to be 50, but you got to find K. So once you find K, you can answer anything you want. So it's very, very similar to what we did, where we had to find K first, and then you're fine after that. All right. So the next thing is looking at this limit of growth idea. Okay, so let's do this. So if you go into this course, like you would watch the videos or get stuff or whatever. Okay, here, I'm just going to do this, I think. I thought my PCC was on here. I guess not. So what we're looking for is this under contents or content. Okay, we're looking for this thing called growth. All right. So we're going to go to that. There's test 2 review, by the way. Growth. So I'm going to click on that. And for all you biologists here, all getting excited. All right. Okay. So this does a pretty decent job of explaining and looking at population growth. So again, this is real similar to what your little project thing has to do with, particularly at the end when you're asked questions about the limit of the growth. All right, so there's a couple of them on here. I'm just going to do this one here where it says logistic growth and launch that. Okay, I'm just going to click on this, and it worked at home. I'm hoping it works here. I'm pretty sure I did it once before with somebody. Yeah, it does. Okay, so did everybody find this here? Are we good? I can wait. So it was under content, right, and growth. So there's 2 different populations here, a red and a blue, all right? And we can play with this a little bit. It gives you a couple different sizes, a population size, a growth rate, and a per capita growth rate. So for example, let's just play with this, run it a little bit here. So these are both 5s. I got a 1.2 and a 1. Let's see what happens. I'm just going to go. All right, and I'm going to pause it here. So here's my red population and my blue, all right, and I can see that, you know, I'm getting more and more of these things. The population size is increasing, all right. Blue's decreasing or increasing, but a little bit smaller, but it's still going. So the question is that if this models, you know, a growth of a population, is there an actual limit? So if this was like fish in a pond, okay, or you know, deer in a area, a certain area, maybe like a wildlife area, something like that, okay. Anything where you have a population, but you have some limitation on size. All right, so if I just continue to go here a little bit more, okay. And what happens is that we see that this thing over here starts to flatten out. Okay, I wish I could click somewhere and not have this. So it starts to flatten out here. There's the blue one, and here's the red one. Okay. So as with most populations, or even like diseases and so forth, you know, they reach a certain limit. Okay, they're going to reach a certain number of cases or a certain population, and it's going to limit out. And you know, a really good example of this is sicknesses like the flu viruses that went around. Okay, the you know, the AIDS virus is a really good example of this. If you go back and look at that data, you know, it takes off, and you know, how many of you remember, you know, in the 80s when they had that big scare of that? It took off exponentially, but then it started to level off, okay, because of different situations, obviously awareness and so forth. But so the number of, you know, growth levels out. And so this is called what we call logistic growth, because it starts off as exponential and it starts to level out, sort of like a logarithm does. So it's almost like combining the 2 things, an exponential and a logarithm. All right. So I'm going to go back and click on this, and if we play with these, all right, first of all, what do you think this value here might represent? These first values here.
Initial value.
Yeah, I mean, initial population. Notice I got 5, so it's 5. So if I come over and say, you know, I'll start out with 20, all right, and maybe I'll leave this one a 5, okay, and then if I go, all right, I can see that, as I would expect, even though I started off, you know, I'm filling it up pretty good here, but even with that, I'm not a whole lot more than the blue. Okay, even though I started out with more. You think maybe you'd have more, you'd end up having way more, but you really don't. Kind of interesting. All right, so I'm going to push this setup and go back to that. All right. Okay, what about the R? What do you think that represents?
Either the factor or the rate.
It's right. It's the rate. Okay. So for example, if we just make this boring, let's see if I can click down to here and put that at 0 and go. Look what happens. The blues never go anywhere because they're not growing. Okay. So that is just your rate. Now notice it's not your factor. Okay, it's that rate. So if we have nothing growing, obviously it's 0. All right. So let's make this something a little bit more exciting. Oops. So maybe like 0.50 or something like that. Now this one's growing quite a bit more. Okay, so I'm going to go again. All right. And I'm getting more, but see how much difference it is down here on the bottom with that rate, which is probably what you would suspect, right? Is that, man, that red one's going to grow quite a bit faster because of the difference in the growth rates. Okay, so they have a much more significant impact on it than what we start out at. Okay, so I'm going to set this back up again. Make that about 0.8. Maybe I'll drop this one down just a tad bit. Okay, what do you think the K stands for? Well, let's try this again. Yeah, look at how it's curving here, see? And it's getting very, very close to that 500 number. All right. Tells you what the red is, tells you what the blue is. All right, where are we at? It doesn't tell you exactly. Time is 500. Okay, we've exceeded that now. All right. So yeah, that is your what we call the carrying capacity. Okay, so that's how much that can hold. All right, so if this is a pond with fish or whatever, or an area with wildlife, you can only sustain so much. All right, and that should make sense to you. So if we increase this, right, then, and I go back to setup and run it, right, that red one should be a little bit higher before it starts to level off. And it's kind of interesting that and it's hard to model it with these exponential equations, but with something like a sequence or a series, it's kind of interesting because some populations will oscillate between that carrying capacity and kind of bounce back and forth. They actually won't level out at it, they'll just kind of bounce at it. All right, it's kind of interesting how that happens. Okay, so again, here you can see that this is about 745 and so forth. All right. So what does those equations kind of look like? So let's say that we play around with this a little bit. All right. And Actually, growth one. So let's go ahead and try that out. So it was something like this. So remember, that's your initial value, okay? So that's why I got that in there. E to the KT, all right? So I got to find K again. See how it's always coming back to the same problem that we've had, right? So how do we find K? What are we going to do? Well, we got numbers, right? We've got numbers here. So let's use them. Let's use the 12 one, for example, okay? If I'm going to deal with the 12, where's the 24.6 going to go? Yeah, 24.6 is going to go there. 20 is going to go here, okay? I don't know what K is, but I sure in heck know what T is. And so now we just got to find K. So we do exact same thing that we did before, okay? So go do it. Go find it. Go find K. All right, and let me know what you get. All right, this is better than doing problems. Bless you. Okay, go find K. You've done about 3 of these. Always the same thing. Let me know what you get. Anybody get a K yet? 0.017. Okay, cool. Y equals 20 E 0.017 T. All right. So neat. Here's what I'm going to do. I'm going to go here. Come on. Y equals 20 E 0.017x. There it goes, just as I would suspect, goes right through those. Okay, and it's growing and growing and growing and growing and growing and growing and growing. All right. Okay, there's that. That's pretty neat. But problem is we know that that's not what happens. Is that as we go here, okay, our equation probably fits that pretty dang well, but it doesn't take into effect that like all populations or diseases or whatever, there's going to be some leveling off. All right, and this is going to occur. So we have to, you know, how does that factor into our equation? All right, stop this. Okay, so let's talk about that. So here we go. Back to this. Okay, so how do we limit out growth? We use this logistic idea. All right, and they tell us, and if you want to know, it's on page 354, but you don't have to go there if you don't want to. They give us this equation here. And all logistic equations look very similar to this. Okay, so here's it is. P of t equals c over 1 plus a times e to the negative bt. All right, and here's what it says. It doesn't really, well, it does. So c is the carrying capacity. It tells you this underneath it. All right. And then it says that A and B are constants. Where is no B? Oh, sorry, K. I called it K. They called it B. So there's some type of a constant, all right? So let's play with this. So let's find an equation that models that red population data, all right? We're going to do that. And we can, because here's what we know. We know what C is, right? Because I ran the program and I know what C is. So let's see, I'm going to just sit back real quick and we'll come back to this. Come on. And 750, all right? So I know that the carrying capacity is 750 because I told it to be 750. Now you might not know what the carrying capacity is, all right? So you might have to guess at that a little bit. 1 on the bottom plus A E negative K T. All right, so now what we want to do is we want to find the rest of the stuff. We got to find A and we got to find a K. All right, so to find A, here's what we're going to do. We're going to use the initial value. All right, you're going to use your initial value. So here's 20 is going to go for P of t. We're going to use the initial value 750 over 1 plus A E negative K 0. Because t is 0, that's our initial value. So watch what happens here.
Where did you get 20? Or did
Because the initial value is 20.
oh, that's basically, sorry.
I know, that's all right. What is anything to the 0 power? 1. Okay, so this is exactly like that second to last question that you guys have on your little project thing, okay? Exactly. So, because it's going to ask you to find this equation, all right? So, anything to the 0 power is 1. Oh, so that means that this is 1 because e to the 0 power is 1. Well, that makes this really nice because now I have 1 plus a times 1. All right, so it's just 1 plus a. And that's what I have. All right? So anything to the 0 power is 1. So now I just have 1 plus a. And I can figure this out. I can use anything you want. You can use some cross multiplication. Okay. You can divide by 750. Doesn't really matter. So many different things you could do. Okay, so we cross multiply here. 20 times both of these, 750 there. I subtract. Now I'm going to divide, and I can figure out what A is. All right. Whatever 730, so see 36.5, I think it is. Because it's just 73 divided by 2. So there's my A value. All right. So now I have population of the reds is equal to the carrying capacity, which I set to be 750. 1 plus. I have an A value now, 36.5. E to the negative KT. So what did we do? We went ahead and we used the initial value to figure out what A is. All right, because anything to the 0 power is 1. It works out real slick. Now, we got to find K, right? So again, that's been our mission, find K all night long. That's what we've been doing. And how did we find K? What are we going to do? How have we been doing it all night?
Put in a value here.
Put in a value. Look, we don't want to use the initial value. That's not going to get us anywhere. But we got 4 other values we can choose from. All right. Or you can even go back in there and find another one. Whatever you want to do. All right. Last time I used 12, so I'm going to use 12 again. All right. So 24.6 is going to go here. Equals 750 over 1 plus 36.5 times E to the negative K, and T is 12. All right. So I'm doing the exact same. See, it's been this over thing where we're just substituting a value in to find K. All right. It's just it gets a little more complicated every time we do it. Notice here again, I'm just going to do some cross multiplying here. But I'm actually not going to multiply this all the way through yet. Okay, I want to pause here for a second so you can see kind of what we're doing. So you can read and look. Now I could distribute the 24.6, but I don't think I will. I think I'm just going to flat out divide it right away. I'm going to need help on that. I don't know what that is. How much?
3.0487.
Sweet.
Oh, wait,
That's not right?
30.49.
3. Okay. So we're really close, all right? Just going to get rid of that. And here we are down to that same equation that we had, the whole time, okay? We just need to divide and then log both sides. Okay, so if I put that whole mess, this thing right here, into Desmos, I'll get an answer for K. All right, the natural log of 29.49 divided by 36.5, divide all that by a negative 12. Somebody can tell me what they get for K.
0.017.
How much?
0.017 or 0.018.
0.18. Okay. So, there it is. All right. And now, again, you can answer any question that you want because your population, okay, 750 over 1 plus, let's see, I gotta remember what A was, 36.5 e to the negative 0.017 t. Okay, so if I go back and graph, if I took all those red data points and put those into Desmos and graphed it, we get a darn good fit. All right, we would. It'd be pretty dang close. So that's a logistics. So let's just take a look at it real quick. I just want to do it anyway. I'll come back to this. Come on. There we go. Let me go back to this. I'll put this guy in here. Okay, there's our, and there it is. Okay, you can see it flattens out right at 750 and bingo. So there's our logistics. Okay? Now, let's say, and this is the second part, this is the very, very last question where it says, how do I find, and let's go find an equation. Because when you do this with your project data, because it's not, this was nice stuff, right, that the computer generated. Yours isn't like that. It's real data. So your logistic equation you come up with, and you graph it, you're probably going to be a little disappointed, saying, wait a minute, I did all that work and this doesn't fit very well. Okay, so let me show you how to fix that. All right. So what I'm going to do is just add some few points here. 250 and 494. 250 and 494. Add another one. 370 and 702. 702. And let me add one more here. 761. All right. So I'm going to wipe that out. Okay. So here's what we're going to do. We're going to find, okay, an equation that matches this thing. All right. We didn't know what we did. All we have is we got some points like this, and we know it's logistic. All right. So what I'm going to do is show you how to do it on Desmos. I can't show you how to do it on Desmos on my tablet when I record it. But what we'll do before we write it is I'm going to end this video and then restart another one and kind of talk people through it and so forth. All right, by just writing things down. But here's how you actually do this. All right, so here's our numbers in a table, x1, y1. Okay? So we're going to go y1. All right? Then you're going to use something called a tilde. All right, so the tilde, if you're using your keyboard, is a shift and the button next to the 1. Okay, if you're going to use this, you're going to use this thing right here. I think that's your tilde right there. Okay, but you got to use that. Okay, now I'm going to let Desmos do the work here. I'm going to put C divided by parentheses 1 plus A, because I don't know what A is, right? That's my constant, right? E to the K, and then I have to put X1 here because it knows that I want to use these numbers. Okay, I better put a times there because I'm not liking that very much. All right. So here's what it comes up with. This is not very good at all, so I don't know why it's giving me this crappy thing here. You can see this is a terrible fit. Let's try putting 745 in there, see if we can help it out a little bit. There we go. So you'll probably have to drop your carrying capacity in there, but you can try without. All right. So what it does is it tells us that A is 36.5 and K is 0.01. We already found this by putting that carrying capacity in there, but you're not going to have that luxury to where you might not be able to do it. In fact, I know your equation is going to come out to be not very good, but if you put a C here, it'll probably figure out what that carrying capacity is because you're going to have better data than what I do, because I just put a whole bunch here and some at the end. If not, you can play with the C value and get your A and K's to be right. Okay, but here's how you do it. You got to go Y1 because that's what you call these numbers here, X1 and Y1. All right, tilde, and then whatever the equation is. You just type those in and it figures it out for you. All right. Okay, that's called a regression equation, and it will find it for you. Magic.